Bessel's equation. Bessel's equation is a differential equation of the form x squared y2 prime plus x y prime plus x squared minus p squared times y equals 0. Here p is constant. Equation 1. The solution of this equation, as also of certain order equations with variable coefficient, should be thought not in the form of a power series, but in the form of a product of sum power of x by a power series. Y is x to the power of r times sum over k from 0 to infinity of ak times x to the power of k. Formula 2. The coefficient a0 may be considered non-zero due to the indefiniteness on the exponent r. We rewrite the expression 2 in the form y is sum over k from 0 to infinity of a case times x to the power of r plus k. And find its derivative. Y prime will be equal to sum over k from 0 to infinity of r plus k multiplied by a case times x to the power of r plus k minus 1. And the second derivative, y2 prime equals sum over k from 0 to infinity of r plus k times r plus k minus 1 times a case times x to the power of r plus k minus 2. Put these expressions into equation 1. Put these expressions into equation 1. We will have x squared times sum over k from 0 to infinity of r plus k times r plus k minus 1 times a case times x to the power of r plus k minus 2 plus x times sum over k from 0 to infinity of r plus k times a case times x to the power of r plus k minus 1 plus x squared minus p squared times sum over k from 0 to infinity of a case times x to the power of r plus k equals 0. Equating to 0 the coefficients of x to the power r plus 1, r plus 2, etc. to r plus k, we get a system of equations. R times r minus 1 plus r minus p squared, take it into bracket, multiply by a0 equals 0, or r squared minus p squared times a0 equals 0. Then r plus first times r plus first minus p squared times a first equals 0, or r plus first r plus 1 squared minus p squared times a first equals 0. Then r plus 2 times r plus 1 plus r plus 2 minus p squared times a2 plus a0 equals 0, or here plus r plus 2 squared minus p squared times a first plus a0 equals 0. Etc. R plus k times r plus k minus 1 plus r plus k minus p squared times a case plus a k minus second equals 0, or I will write down here r plus k squared minus p squared times a case plus a k minus second equals 0. All of this denote by 3. System 3. Let us consider the later equation. R plus k squared minus p squared times a case plus a k minus second equals 0, and denote this 3 prime. It may be rewritten as follows: r plus k minus p times r plus k plus p, it is difference of squared, times a case plus a k minus second equals 0. It is given that a0 is not equal to 0. Hence, r squared minus p squared must be equal to 0. Therefore, r first is p, or r second is minus p. Let us first consider the solution for r first is p is greater than 0. From the system of equation 3, we determine all the coefficients a first, a second, etc. in succession. A0 remains arbitrary. For instance, put A0 equals 1. Then a case must be equal to minus a k minus 2 k minus second over k times 2p plus k. Assigning various value to k, we find a first is 0, a third equals 0, and generally all odd a equals 0. A second equals minus 1 over 2 times 2p plus 2. A fourth equals 1 over 2 times 4 times 2p plus 2 times 2p plus 4 etc. A maybe 2 nu equals minus 1 to the power of nu plus 1 times 1 over sorry 2 times 4 times 6 times etc. times 2u times 2p plus 2 times 2p plus 4 etc. times 2p plus 2 nu. Note all of this. Number 4. Putting the coefficient found into 2 we obtain y first equals x to the power of p times bracket into bracket 1 minus x squared over 2 times 2p plus 2 plus x to the power of 4 over 2 times 4 times 2p plus 2 times 2p plus 4 minus x to the power of 6 over 2 times 4 times 6 times 2p plus 2 2p plus 4 2p plus 6 plus etc. Close the bracket. Number 5. All the coefficient a to nu will be determined since for every k the coefficient of a k in 3 r plus k squared minus p squared will be different from 0. Thus, y first is a particular solution of equation 1. Now you have 5-minute rest and then we continue. Do you understand me? Is it clear? 5-minute rest for you. Are you hear me?
Yes, yes.
Okay. Let us further establish the condition under which all the coefficient AK's will be determined for the second root R second equals minus P as well. This will occur if for any even integral positive k, the following inequalities are fulfilled. R second plus k squared minus p squared is not equal to 0. Formula 6. Or R second plus k is not equal to p. But p is R first. Hence, R second plus k is not equal to R first. Thus, condition 6 has in this case equivalent to the following. R first minus R second is not equal to k. Where k is a positive even integer. Where k is a positive even integer. But R first is p. R second is minus p. R first minus R second is 2p. Thus, if p is not equal to an integer, it is possible to write a second particular solution that is obtained from expression 5 by substituting minus p for p. y second equals x to the power minus p times 1 minus x squared over 2 times minus 2p plus 2 plus x to the power of 4 over 2 times 4 times minus 2p plus 2 times minus 2p plus 4 minus x to the power of 6 over 2, 4, 6 times minus 2p plus 2 minus 2p plus 4 minus 2p plus 6 plus etc. Formula 5 prime. The power series 5 and 5 prime converge for all values of x. This is readily found by D'Alembert test. It is likewise obvious that y first and y second are linearly independent. 5 and 5 prime converge. By D'Alembert test. Then y first and y second are linearly independent. Linearly independent. The solution y first multiplied by a certain constant is called a Bessel function of the first kind of order p. We now write down this. The solution y first multiplied by a certain constant is called A Bessel function of the first kind of order P. A Bessel function of the first kind of order P. And is defined by the symbol G P. The solution 1, 2 is denoted by the symbol G minus P. Minus P, it is lower index, and P2. Thus, for P not equal to n integer, the general solution of equation 1 has the form y equals c first times g fifth plus c second times g minus fifth. For instance, when p is 1 over 2, the series 5 will have the form x to the power of 1 over 2 times 1 minus x squared over 2 times 3 plus x to the power of 4 over 2 times 4 times 3 times 5 minus x to the power of 6 over 2 times 4 times 6 times 3 times 5 times 7. Plus etc. Equals 1 over square root of x times x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial plus etc. This solution multiplied by the constant factor square root of 2 over p is called Bessel's function y with the lower index 1 over 2. Write down this. This solution I cannot write down. Maybe I send to you this board and clean it right now. Now I give you it. One minute, please. Can you see this board in the chat?
Yes.
Okay. It means I can clean all of this. Don't want to clean. Oof. 1 minute. Don't want to work. Okay. End it. And continue. The latest solution multiplied by the constant factor square root of 2 over pi is called Bessel's function g with the lower index 1 over 2. We know that the bracket contains a series whose sum is equal to sine of x. G with lower index 1 over 2 of x is square root of 2 over pi x times sine of x. In exactly the same way, using formula 5 prime, we obtain g with the lower index minus 1 over 2 of x equals square root of 2 over pi x times cosine of x. The general integral of 1 for p is 1 over 2 is y equals c first times g with the lower index 1 over 2 of x plus c second times g with the lower index minus 1 over 2 of x. Now let p be an integer which we shall denote by n, where n is positive number. The solution of 5 will in this case be meaningful and is the first particular solution of 1. But the solution of 5 prime will not be meaningful because one of the factors of the denominator will become 0 upon expansion. For positive integral p equals n, the Bessel's function g n's is determined by the series 5 multiplier into the constant factor 1 over 2 to the power of n times n factorial. When n is 0, we multiply by 1. It means gn's of x equals x to the power of n over 2 to the power of n times n factorial times 1 minus x squared over 2 times 2n plus 2 plus x to the power of 4 over 2 times 4 times 2n plus 2 times 2n plus 4 minus x to the power of 6 over 2 times 4 times 6 times 2n plus 2 times 2n plus 4 times 2n plus 6 plus etc. Or g(n)s of x equals sum over nu from 0 to infinity of minus 1 to the power of nu over nu factorial and n plus nu factorial times x over 2 to the power n plus 2 nu. Formula 7. It may be shown that the second particular solution should in the case be thought in the form k(n)s of x is g(n)s of x times natural logarithm of x plus x to the power of minus n times sum over k from 0 to infinity of b(n)s times x to the power of k. Putting this expression into 1, we determine the coefficient bk. The function k(n)s of x, this function, will the coefficients thus determined multiplied by a certain constant is called Bessel's function of the second kind of order n. Write down this. The function k(n)s of x with the coefficient thus determined multiplied by a certain constant is called Bessel's function of the second kind of order n. Bessel function of the second kind of order n. This is the second solution of one which with the first one forms a linearly independent system. The general integral will be of the form the general integral y is c first times g n's of x plus c second times k n's of x. It is number 8. We note that limit as x approaches 0 of k n's of x equals infinity. Hence, if we want to consider the final solution for x is 0, then we must put c second equals 0 into formula 8. Consider the example. Find the solution of Bessel's equation for p is 0, y2 prime plus 1 over x times y prime plus y equals 0. That satisfies the initial condition for x is 0, y is 2, and y prime is 0. That satisfy the initial conditions for x is 0, y is 2, y prime is 0. Solution. From 7, we find one particular solution. g0 of x equals sum over nu from 0 to infinity of minus 1 to the power of nu over nu factorial squared times x over 2 to the power of 2 nu equals 1 minus 1 over 1 factorial squared times x over 2 squared plus 1 over 2 factorial squared times x over 2 to the power of 4 minus 1 over 3 factorial squared times x over 2 to the power of 6 plus etc. Using this solution, we can write a solution that satisfies the given initial conditions, namely y is 2 times g zeros of x. We will have to find the general integral of this given equation. We would seek the second particular solution in the form k0 equals g0 times natural logarithm of x plus sum over k from 0 to infinity of b k's times x to the power of k. Without giving all the combinations, we indicate that the second particular solution, which we denote by k zeros of x, is of the form k zeros of x equals g zeros of x times natural logarithm of x plus x squared over 2 squared minus 1 over 2 factorial squared times x over 2 squared times 1 plus 1 over 2 plus 1 over 3 factorial to the power of 6. Oh, 2, sorry. Times x over 2 to the power of 6 times 1 plus 1 over 2 plus 1 over 3 minus etc. This function multiplied by some constant factor is called Bessel's function of the second kind of order 0. Write down this. This function multiplied by some constant factor is called Bessel's function of the second kind of order 0. On this moment our lecture ended. If you have any question to me, I ask for you, or find for you. Sorry. Not question.
No, thanks.
Have you good weekend. Have you good day. Goodbye.
Bye-bye.
Bye bye.